Another sort of feature we can look for in a correct partial fractions decomposition, we have as many coefficients as we have powers in the bottom. Yeah.
So in the numerator, when do you add the second term? Like, you know what I'm saying? Like, we went from single terms for ABC.
It's because these are irreducible quadratics, okay, as opposed to linear factors. No, why would I mean, this is, yay, algebra. Why we do this? I mean, why do we care about this algebra? Can you understand why? Yeah.
It's a whole lot easier to integrate each of those terms individually than trying to do the original one.
Right, exactly. If I asked you the integral of this, now, you still need to figure out what A, B, C, D, E, F, G, H, and I are. And I don't really want to do that for this example because that would be 9 equations in 9 unknowns. Unpleasant. But my point is you can find these A, B, C, D, E, F, G, H, I. It's possible. And once you do, integration's a breeze because you can integrate that. You can integrate that. You can integrate that. You can integrate this. It's a combination of an arctangent substitution and a u substitution for the x over x squared plus 4, right? You can integrate this. Again, you can make a u equals x plus 2 squared plus 1 substitution to take care of this term. And then the other piece is an arctangent substitute. It's an arctangent integral, or you could look at it as a tangent equals x plus 2 substitution to do this guy, right? This guy, again, you could make a tangent equals x plus 2 substitution to do this one as well. So if you look at all these terms, we know how to do these integrals. You may not be comfortable yet, but you can do these with the techniques we've already gone over. So partial fractions, what it does is it takes an arbitrary rational function and it converts it into a sum of what I call basic rational functions. The basic rational functions being things that we can actually integrate. And that's the method. Right? Now this would not be a problem I'd actually give you on a test, obviously, because it's awful, right? So let's look at an actual example if I still have time, which is debatable. Haha! I was talking faster than I thought. Example 1, pretty standard. Integral dx over x squared minus 3x plus 2. There we go. So this one you probably could do this with like one of our hyperbolic this or that integrals, right? Like we already have a method to do this even, but I'm going to do it with partial fractions because I think it's helpful, important for you to see it. So we've got x squared minus 3x plus 2, right? Also known as 1 over what? X minus 1 times x minus 2. Am I right? Hopefully I can factor. I don't know. Yeah? No? Yeah. It's been a long week. I mean, what's, no? Yeah. All right. A over x minus 1 plus b over x minus 2. I'm just excited because I didn't end up with secant to the fifth and anything today. So I feel better about my day. So there you go. A over x minus 1, b over x minus 2. And then the question is, what are a and b? We need to figure that out. So the way to do that, standard way, just multiply by the denominator. Multiplying by the denominator gives me this. Do you see why? When I multiply, I have a cancellation, right? Multiplying by x minus 1 times x minus 2, the x minus 1 cancels with the a term, right? And the x minus 2 cancels with the b term. So what do I make for a and b? Well, my suggestion for this kind of problem is the easiest way to do it is just put in values. X equals to 2 is a very nice thing to look at because that gives me 1 equals to a times 0 plus b times 2 minus 1. So yeah, b equals 1. Okay, that was not too bad, right? I mean, like the algebra here was not that bad. X equals to 1, how about that? Why am I looking at 1 and 2? Do you see why I'm doing that? Because I know it makes those factors 0, which makes the equations way easier to think about. Put in x equal to 1, I get 1 is a times 1 minus 2. That's 0, right? A is equal to, looks like minus 1, right? Because minus a is equal to 1. This is great. This means that we can trade this unpleasant dx over a quadratic for the rather agreeable 1 over x minus 2 minus 1 over x minus 1. Yay. And so doing, we can just integrate, right? If you like, you could think about making a u equals x minus 2 and a w equals x minus 1 substitution, right? That means, anyway, getting to the point here, that's natural log the absolute value of x minus 2 minus the natural log the absolute value of x minus 1 plus a constant. And there you have it. I do think that we covered this integral by another method in Chapter 5, but I will say this. This is the right way to do this integral. Like, this is the easier way, I think. I could be wrong, but it depends on what you know, right? You know, if you're like a Chapter 5 ninja, you're already like, I already know how to do that integral. I learned it. It's inverse hyperbolic secant, or whatever it is. I don't remember. Something like that. Shall we do another? Let's do another. Integral of x plus x squared dx over x plus 1 squared times x squared plus 1. Let's see here. So I need to come up with my partial fractions decomposition. Here's what it's going to look like. X plus x squared over x plus 1 quantity squared times x squared plus 1. So I'm going to have a over x plus 1 plus b over x plus 1 squared plus cx plus d over x squared plus 1. Do you guys have any questions about the big blue equation? There's probably a nicer formatted version of this in your book, yeah?
I do have a question, but it's not about that. With over there with the a over x minus 1 plus b over x minus 2, I didn't think that you were allowed to choose one. Have x be one thing in one part and x be another thing in another part, like
Oh, well,
x be one
this,
in one part and x be two.
all right, so, you know, like, make up my mind. You're like, make up your mind. Is x 2 or is it 1, right?
I didn't think you were, I guess, allowed to do that, or
Well, the thing is,
that.
this is an identity in x, right? So we're actually looking for a and b such that this is true for all x, not equal to 1 or 2. The real question is, why am I allowed to plug in the 2 points where this isn't defined for and yet come into meaningful information about it?
Yeah.
I mean, but that's not your question. This is an identity. So this holds for not one x, but for lots of x. So we can,
I thought that the x out of it, or a x minus 1 and the x minus 2, that x has to be the same for both.
x is a variable, so no. I don't know, I'm not sure how I can talk you out of that at the moment. Look, I mean, the proof is in the pudding, so to speak, right? I mean, I've claimed that this is algebraically the same as the integrand that we started with, right? How do you undo? How do you make this into a, what do we do? Common denominator, right? So this is x minus 1 minus x minus 2 divided by x minus 2 times x minus 1, right? Common denominatoring, if we're allowed to say that or not. So this is, the x's cancel, and you got, what you got? You got minus 1, minus a minus 2, otherwise known as 1. And downstairs, we got our x squared, minus 3x, right? Plus 2, what do you know? So, I mean, you can debate my methods, but you have to agree that the answer that I found is in fact algebraically legitimate, right? We all agree that this is making a common denominator and that I have reproduced the integrand by making a common denominator of my partial fractions decomposition. What partial fractions is it's uncommon denominatoring. it's reverse common denominatoring. It's like, how would you change it back into a sum of things that you then could put together to make a common denominator, right? It's an unfamiliar bit of algebra. It is in some college algebra books, but I was not taught it in college algebra personally. You know, I don't know. So this is the partial fractions. The best answer I have to your question is it's not for a fixed x that we're looking, it's for a variable x that we're trying to find a and b. Let me get, I gotta move along here, otherwise I'm not gonna finish it. This, so what we do is multiply both sides by the denominator. That gives me x plus x squared is a times x plus 1 times x squared plus 1 plus b times x squared plus 1 plus cx plus d times x plus 1 squared. And this one, the algebra is a little bit fussier. So two easy things to do, which again, I mean, there's something kind of something kind of hinky here, because I mean that equation is not defined for x equal to minus 1, and yet I'm putting in minus 1, and it's going to give me useful information. That's a mystery. Maybe you can solve it why that works. Let's see, that's 0. That's not 0. That's 2. And that's 0. Oh, that's 2. Okay, so we get 0 equals to, what you got me? 2b. That's 4. Oh, that is 0, right? This is x plus 1. I'm a victim of my own bet habits. Yeah, this is 0 as well. So we only get the b term. Oh, I guess b0, huh? What's up? Yep. Oh, I made it up. But it's just a generic, like it worked over here. Take zeros of your factors, nice things happen. Unfortunately, we're fresh out of zeros now for this one. Unless you want to go complex, yeah.
Why is it x plus 1, cx plus d times x plus 1 squared not?
That is the partial fractions decomposition. That is what comes of having such a term. The difference is, this is a repeated linear factor, so it produces these. This is a not factorable quadratic, so it produces that pattern. I mean, ask that question again tomorrow. I'll try to answer it again in a different way. But what's next? I mean, what you could do, past this point, is this is an equation, so we can look at like, what's the coefficient of x? Or how about this? Let's go lower. Let's look at the coefficient, the constant terms. What's the constant on the left-hand side? 0, right? Is there any constant over here? Nope. How about the constants over here? What's the constant terms? I've got this 1 times a. I've got an a. Is there any constant term here? Oh, plus b. Any constant term here? Looks like we got a plus a d. All but degree. Let's see here. Anything else? I think that's it. Of course, the b is 0, right? How would c get into the story here? C's got an x next to it. It can't be just 1, right? See what I mean? See here, so a equals to minus d. That's useful but not done. How about x? Let's look at the coefficient of x. X over here, we've got a coefficient of 1. Coefficient of 1 on the left-hand side. Where are there x terms on the right-hand side? I've got a times x times 1. I've got an a. Anything else x here? Ax. What's that? Oh, but that's x squared, not x. So there's nothing here. And also b was 0, so we should stop thinking about this one. 0. Save our time. Over here, now we got that cx term. Cx times 1. Now I should probably write this out. X plus 1 squared is what? It's x squared plus 2x plus 1. That might keep me out of trouble here. So I got c, yeah, plus c. And what else do I have x? I've got d times 2. I got a plus 2d. Anything else? Think about multiplying this out. Any way I can get x's? I think that's it. How about x squared? We got a 1. Coefficient of x squared is 1 over here. And, oh, a, thank you. Anything other x squareds? No, that's 0. I don't care about that. We got a d plus d from dx squared. Anything else? Oh, yeah, plus 2c, right? Because 2x times cx gives me 2x squared, so that gives me a 2c. Now we just need to solve these equations. Let's see here. This says what? A is minus d. So what's this give me? 1 equals to c plus d. This gives me what? 1 equal to a plus d was 0, right? So 1 is equal to 2. Oh, 1 is equal to 2c. Hooray! So c is equal to a half. And then what's that make d? Yeah, d has to be 1/2, which means a is minus 1/2. Then what do? You take those, plug these numbers into here, put that into the integral, and you can do it. That's partial fractions. Sorry I'm a little bit hurried, but it's your fault. You asked me so many homework questions. And hard ones too. I blame all of you. Mostly the third row. No, I'm just kidding. So tomorrow, yet more partial fractions. Woo! Yep. Ah! We'll never know.
It's really just like the pattern itself. I think it's just the pattern itself.